In this tutorial, we'll review the Adam optimizer, which is used during the training of deep neural network. We're also going to code it with numpy. You'll see it's not that complicated. Adam is an historically important optimizer in the gradient descent family because it mixes the best idea of previous variant like momentum and RMS prop. Even today, its variant, Adam W, is the one that is mostly used in training deep neural network. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who loves to teach. Do consider subscribing to the channel to learn technical topics related to machine learning. So let's review quickly where exactly Adam will fit in a deep learning setting. So let's start with the basic neural network. Data comes in into the input layer. It gets linearly transformed by bias and weight for each neuron. A nonlinearity is introduced after that, usually a ReLU. This process is repeated at each layer until the output layer, which output the class or number for the data point. Now that we have that label, we calculate the loss, which is task dependent. All previous gradients are set to 0 before a new gradient with respect to that loss get calculated starting from the end of the network until the first hidden layer. When all gradients are calculated, it's time to update the weight with the optimizer. It will take all of the gradient information per weights, and based on the optimizer parameter and historical information, like past gradient, weight will get updated by a tiny small amount. Adam is one such optimizer. Adams means adaptive moment estimation and is a mix of RMS prop and the momentum algorithm. In a nutshell, in Adam, there's running averages that are used with exponential forgetting parameters, like from RMS prop, that are applied to the gradient and its second moment. Let's dive deeper into the formula and the core element that we're taking from the momentum algorithm and then the RMS prop algorithm. If you were to just look at this, chances are you will not be able to understand what's going on. We can pick each of the things off one by one. If you look at the meta structure here, you have the classical weight from the previous iteration, learning rate, and then something that has within it some gradient information. So that's just the overall structure. It doesn't change, it's the same thing. How you need to understand Adam is you need to go back and then follow the thread to find each of the bit. So this bit over here, right? This come from this influence, so the momentum, right? We're gonna see it and we're gonna go through it. It comes from here. And then this other bit over here, right? So this one, it comes from the RMS prop lineage, right? Which also come from Adagred. So this is here, and then like this interaction over there is the interaction from momentum, and this interaction over here is the interaction from RMS prop. That's in a nutshell what you're seeing. Now you might be asking, why do we have this then? Where does it come from? It's duct tape, right? This is duct tape to a bias correct the initialization because it starts at 0. And if it starts at 0, it becomes unstable. Basically what you have here is these two parameters, beta 1 and beta 2, which are usually under 1. They have to be under 1. So at the beginning, you're gonna have b exponent 1. You're gonna have 1 minus b exponent 1, which is like something like 0.9. So you're gonna kind of scale this element. But as this increase, let's say be 100, whatever, you're gonna have to do 0.9 exponent something. So it's gonna get, it will tend to 0, right? Which then you will do 1 minus 0. 1 minus 0, it will be 1, so this will stop being applied. So it's duct tape at the very beginning. So don't worry too much about that part. So if we look at, take a step back at the stochastic gradient descent, you have the simplest format, which is you have the weight, you have the learning rate, and then you have some amount of gradient here. That's roughly it. And then you have a batch that you're gonna use to estimate that gradient. Momentum, what it does, right? You still have this structure, right? You have that structure over here. It's also taking into consideration the past update that you did. So whatever you were going before, you're still gonna kind of go into this direction. So why it's called the heavy ball method, because you can think about it as a ball rolling, and if it was rolling in this direction, it will keep rolling into this direction unless you have some motion that push you in another spot. And you have this new parameter, which is alpha, which is an exponential decay factor between 0 and 1 that will determine the relative contribution of the current gradient and earlier gradient to the weight change. So this alpha will tell you how much you should take into consideration the past versus the present. So if this is very, very heavy, you're gonna have a lot of momentum on like the previous direction, which will make it hard to change to course correct. But if it's very light, you will have some impact, but like not that much. So this part is effectively what is over here. So this was the previous, what we call moment, right? From like the previous, not tick, but like previous time. And then this beta 1 is how much you should weight the previous time. And it's usually a 0.9, so you kind of weight it heavily. And this delta L, same thing as delta Q, which is the gradient, right, at this time. And you're gonna weight it at 0.1 here. So you're gonna take some of it, but you're gonna still go into mainly in the direction here. To have a big impact here, the gradient at whatever direction need to be very high. So if we look at this other bit here, we have to rewind like 2 times before we're gonna get there. So let's start with AdaGrad. AdaGrad is kind of a older idea from 2011, right? Adam was from 2014, I believe. So in 2011, what the idea was that we're going to use stochastic gradient descent, but we're going to scale the parameter learning rate per parameters. So this is kind of useful when some parameters should have higher rate of change than other one, right? Depending on their relative change over time. So the core idea is that, roughly speaking, if it will take into consideration the parameter dynamics. So if the parameter has very hectic changes, we're gonna want to dampen this effect so that like we don't like move too fast here. But if some parameters have very slow changes or magnitude that are very small, but then suddenly change, we should take that into consideration and do a big step there. So the learning rate will be higher there. That's the rough idea, right? So all of this live into like this vector j, which is the diagonal of this, and then this small j is the gradient. So the gradient iteration t, the diagonal is given by that. So we're using this, the past gradient information, to tell us what we should be doing. And if you look here, basically what we're gonna do, because the only thing that matters is like this diagonal of this this matrix. So this is per parameter, right? We're gonna scale the parameter with the square root of the summation over the past gradient. So if over the course the sum gets very large, it will get dampened a lot. So if the sum is very small, the learning rate will not get dampened as much. So that's the kind of the idea. And here they're saying extreme parameter update get dampened, while parameters that get few or small update receive higher learning rate. This was good, but then Ilya and company did some tweak here on AdaGrad to have a bit of a conceptually, if you think about it, right? The longer the training goes, the more you're taking into consideration stuff that happened way back in the past. So it would be a bit better if you could forget a bit the old past and kind of look more right now what is happening with the current gradient update. So what they introduce here is what is called a forgetting factor here. It's the same thing as here, like exactly the same thing. It's the same idea of having like the gradient squared over here, over there, you have it squared, but then you have a forgetting factor based on like what was there in the past. So this, right? This is what was happening in the past. And you multiply this by this forgetting factor and what is happening right now, right? So depending, you're gonna weight it. And I think the weight that we're using here is 0.999. So we're taking a lot of what happened in the past in consideration. And this, which is the same thing as before, is being divided by the square root of here, just like what happened previously over here. And then this is where this bit comes in, right? You have the gradient squared here, you have your forgetting factor, this is this one. If you think about it, we also introduced a forgetting factor for the momentum, but it's not really a forgetting factor, but like it has the same structure now. And then these two is here, and then this little bit is the same thing as in RMS prop, right? It's just over there. The only thing that is added here is the epsilon, but you should have an epsilon everywhere, which is a small number that like to avoid dividing by 0. So that's that. That's the whole Adam. So I think we're ready to do the implementation. And here I'm going to use a website called DeepML. The link is in the description, which basically has some test cases that you can test with. This is the question that we're going to use. And like, this is the implementation that we need to do. Nothing weird here. It's the same stuff. These will be our input, right? You remember in an optimizer, the gradients are already there for you. You just have to know how to change the parameter based on some sort of information that you already have. All right, so here we are. Here, this is our input. We have the parameters, we have the gradient, we have the first moment estimate, the second moment estimate. So this is the stuff that we're carrying over from previous things. So you have to keep them and you have to like output them again and again. The T is our current time step. You have the starting learning rate here that we're gonna scale up and down. You have the beta 1, which is the forgetting factor for the momentum based type of thing, and the beta 2, which is the forgetting factor for the RMS prop type of thing that we're doing, and then the epsilon. First step here is really to calculate this. So this will be our first step, and our second step will be to calculate that over here, right? And then we're gonna have a third and fourth step, which is to bias correct it, and then the first moment and then bias correct the second moment. Nothing too fancy here. And then the last thing is you're gonna put all of it together. Implementation wise, very straightforward. So if we go over it, so step 1, here we're gonna have the first moment calculation, right? And then the first moment calculation, if you look, we're gonna call it M. We have beta 1, right, times the previous M plus 1 minus beta 1, and then time the current gradient, right? That's roughly it. Step 2 is the second moment calculation. Moment calculation, and it's the same idea here. We have V equal beta 2 times V plus 1 minus beta 2 time the gradient exponent 2. So far, so good. So now we're going to do the bias correction. Bias correction for the first moment. And it's going to be M corrected equal M divided by 1 minus beta 1 exponent t. And this is going to be the same thing for the second moment bias correction. Right, so V corrected, so V 1 minus beta 2 t, and then that, and then we're gonna just put everything together, right, to do one update. And it's gonna be parameter equal parameter minus the learning rate times M corrected. So parameter times minus the learning rate times M corrected, right, this one, divided by the square root of V corrected plus epsilon, divided by V corrected exponent, oops, 1 divided by 2 plus epsilon. Oops. And that's it. And then what we need to return here is our new parameter. We have to return our M and our new V. And don't forget, you don't have to return the bias corrected one, right? You just return the M and V because that's what you're going to use afterward. The bias correction is only for the parameter update. Run that code. And we got it right. So here, this is in the first test case that we had here. And this is for the second test case with a few more parameters. That's it. Coding wise, there is not much to it, right? Even in the formula, there is not much to it. To understand it, you have to take a step back and then look at the whole thing and where each of the ideas come from, right? So if we recap here, you have stochastic gradient descent, right? And then we introduce momentum in one branch, and a second branch here, we introduced like per parameter learning scaling But then we don't want to do the scaling based on the whole history. We want to have a running average that is moving a bit, right, to throw away what was happening in the past. And then this is what you're gonna mix the two of them together in order to do Adam, but you add bias correction to the mix. I hope this was useful. Don't forget to like if it was the case, and see you all in the next video.